Okay. So, I guess midterm is coming up, and today I'll just do a few problems from this problem set, and of course take questions if you guys have some, and yeah. Okay. So I was thinking before we start off on this week's problem set, we could just very quickly do again a problem that was on, I guess, problem set 6, which is, the barbershop problem. Just kind of, it's a very typical problem of continuous time Markov chains and birth-death processes, so it's good to have that one sort of down. So I thought we could start with that and then move on. And I think Ali, my classmate, may have done this when I was away that one time. So if you've seen it before, just bear with me. So this is 613. Okay. So we have a barber shop with a single barber, has room for at most 2 customers. Potential customers arrive at a Poisson rate of 3 per hour. The successive service times are independent, exponential random variables with mean 1/4 of an hour. So I guess we have the model MM1, 2. So we have Poisson process arrivals with rate, I guess lambda is equal to 3 per hour. So lambda is equal to 3. Then we have exponential service times with mean 1/4 of an hour. So I guess what this means is that 1 over mu is equal to 1 over 4. This is the number of servers. And waiting, and this is the waiting space capacity. Okay. And now, so we want to figure out certain quantities here. So let's first define as NT to be the number of customers in the barber shop. So barber shop at time t. And, of course, the state space can either be, we can have 0, we could have 1, 0, 1, or 2. Okay. And now, sort of the first crucial thing is to understand that this is a birth and death problem. Yeah?
Why would it be 3? Because isn't the first being served also times 1?
In the shop. Oh, yeah. Oh. Well, the reason why it's not 3 is that the waiting space is 1. Yeah, sorry. Yeah, that's an excellent point, though. Okay, so So let's see now. The first thing to note is that N of t is a birth-death process. And why is that? Well, we can just, let's look at the transitions between states. So it's state 0, 1, and 2. So we go from state 0 to state 1 with rate lambda. And then from state 1, we go to state 2. We go to state 0 with rate mu1. And then we sort of have the same thing going on here. And now, I guess lambda is just equal to 3. Mu1 and mu2 are equal to 4. And that's basically the end of the problem, because now it's very easy to, once we've determined the birth rates, let's actually put down lambda 0 and then lambda 1, just for the sake of being consistent. So now, now it's sort of a trivial thing to figure out all these questions, because since it is a birth-death process, we know that the stationary probabilities are given by, remember this formula in the book, which is very useful. Oops. So we have this formula, so we can readily, if we know that something is a birth-death process, and if we know what the birth rates and what the death rates are, we can just plug these numbers in and out come the stationary probabilities. So in our case, P0 will just be 1 over 1 plus, and now we have, okay, so lambda 0 divided by mu1, so 3 over 4, plus, and everything else is 0 here. I guess I made this right. So P0 just becomes 1 plus 3 over 4 plus 3 times 3 over 4 times 4. And I guess this is equal to, if you do the math, 16 over 37. And equivalently, P1 is just 3 over 4 times 16 over 37. So this is 12 over 37. And P2 would just be 9 over 37. So we know now the long-term proportion of time that we have no customers, 1 customer, and 2 customers in the system. Okay. So now, let's start answering the questions. So what is the average number of customers in the shop? So in the long run, we have an average of so 0 times P0 plus 1 times P1 plus 2 times P2, which is equal to uh, 30 over 37. Now let's see what part B is asking. So the proportion of potential customers that enter the shop. Well, when will someone enter the shop? It will only be if either there are no people in, or one person is currently being served. So in this case, this will just be P0 plus P1, because you will not enter if the waiting space is also sort of full. So if you have one person also waiting. So this will be equal to 28 over 37. And finally, part C, if a barber could work twice as fast, how much more business would he do? So now barber can work twice as fast. That means that mu1 and mu2 would be equal to 8. So how much more business would he do now? So we can go through the same analysis and calculate new values for the probabilities. Calculate. So let's give them a tilde. So now, as you would expect, probability of the server being empty is less because it can serve more quickly. Or actually, it would be great. It would be more. I'm sorry. Okay. So now, people do not enter with probability 9 over 97. So the served proportion increases to, and people enter with 88 over 97. So so there is a difference. 87 minus 28 over 37. This is equal to so we have a gain of roughly 15%. Because now 15 more out of 100 customers will actually enter the shop. So that's kind of the measure that we use to say, well, how much more business is he doing? Just the difference between the two entry probabilities. So this is a fairly typical problem. If anyone has questions, this is an important one to know. Yeah?
Just one quick thing. talk about birth and death rates. So is the birth rate of going like q of I to I plus 1 and the death rate the like mu of, or the q of I to I minus 1? Is that kind of like synonymous? Because when you say like mu1, mu2 is equal to 4, isn't that the same thing as saying going from state 1 to state 0 at rate 4?
Yeah, exactly. So the question was, are the birth rates and death rates just, if you're starting at state I, is the birth rate qi I plus 1 and the death rate qi I minus 1? And the answer is yes. Okay. So now let's move on to the next problem then. But always remember this. Okay. So now this is another problem that I've seen many times before. So now we have potential customers arriving at a full-service one-pump gas station, the Poisson rate, blah, blah, blah. But customers will only enter the station if there are no more than 2 cars at the pump. Suppose the amount of time required to service a car is exponentially distributed with a mean of 5 minutes. Okay. So this is again very similar to the other problem, right? Because again we have one pump, so this is like one server, and one car can only be served, or there's waiting room for just one car. So here the rate is lambda. Lambda equals 20. The service rate has a mean of 5 minutes, so 1 over mu is equal to, now we're sort of looking at it in terms of hours. So 5 minutes is 1/12 of an hour. And the rest, I think, is self-explanatory. So let's again denote by n of t the number of cars in system at time t. And then n of t is a birth-death process with state space 0, 1, and 2. So again, let's draw the little diagram. 1, 0, 1, and 2. So now we go from state 0 to state 1 with rate lambda 0. And then from state 1 to state 2, rate lambda 1, mu 1, and mu 2. Now let's identify what these rates are. Well, lambda 0 and lambda 1 are just identically equal to 20. And also, mu 1 and mu 2 are equal to 12, because I guess this is, we're measuring everything in terms of hours. So, oops. So they serve 12 cars per hour. And everything else is 0. Okay. It's the same thing. So now P0 will be 1 over 1 plus 20 over 12 plus 20 times 20, 12 times 12. I guess this gives us an answer of 9 over 49. And P1 will be 20 over 12 times P0. And this will give us an answer of 15 over 49. Now, note that I could write this again, but there's a nice sort of recursive way of finding these probabilities. So, P1 is just equal to lambda 0 over mu 1 times P0. P2 is equal to lambda 2 over mu 1 times P1. And there's nothing sort of mysterious about this. If you look at the formula, you'll see how this just readily is obvious. So, in general, a recursive way to find these probabilities, Pn is just equal to lambda n minus 1 over mu n times Pn minus 1. And of course, P0, we start with P0 being this guy here. And this is, of course, consistent with Pn being equal to times P0. Okay, so what fraction of the attendant's time will be spent servicing cars? Well, the attendant will only service cars if, something's at the station, right? So this will just be P1 plus P2. He will not be servicing if the station is empty. So this is 40 over 49. And then part B, what fraction of potential customers are lost? This will be P2. Because if someone arrives and there are already 2 people in the pot at the gas station, well, that person leaves because he can't be served. So this is the answer. Any questions? Pretty clear? Okay. Okay. Well, let's do problem 620. So there are two machines, one of which is used as a spare. A working machine will function for an exponential time with rate lambda and then fail. Upon failure, it is immediately replaced by the other machine if that one is in working order, and it goes to the repair facility. The repair facility consists of a single person. Okay. Okay, so let's first sort of define what we're interested in. So xt is the number of working machines at time t. The state space is 0, 1, 2. No, xt is the number of machines that are down. And this is a birth-death process. Because we can only repair one machine at a time. And of course, only one machine can fail at any particular time instant. So let's figure out the birth rates and death rates. And, of course, we'll talk more about the how exactly something fails and so on and so forth. Okay, so we know that if both machines are working, okay. So we have two machines that are working, and each one independently fails with rate lambda, with an exponential, with a Poisson process like lambda. So the minimum of the two so the rate of the failure, so the minimum, how do I say this? So this rate will be 2 times lambda, right? Because either one or the other can fail. And we're interested in the minimum of the two failing. The minimum of two exponentials, again exponential, would rate the sum of the two rates. So we go from state 0 to state 1 with exponential rate 2 lambda. Yes?
If one of the machines is a spare, it means it's not running. So you only have one machine at time 0. Something else goes.
Yeah, you're right. That's, yeah, so what I said was wrong, because one of them is used as a spare, so birth rate is just lambda. And then once it fails, it's replaced, with a spare machine. So, someone say something? Again, that fails again with rate lambda. And the repairman, I guess, takes exponential time mu to fix the machine. Yeah, so it's simpler than I thought. So starting with both machines at working condition, find the expected value until both are in the repair facility. So let's sort of define Ti to be the time to go from state I to I plus 1. So, in other words, if we're starting with two operational machines, we're interested in, we want to find expected value of this, and its variance. Because t0 plus t1 is the time to go from state 0 to state 1 plus the time to go from state 1 to state 2, which is what we ultimately want to find. And now we can refer back to the book on page, I guess it's on pages 356. So refer to Ross, pages 356 to 359, where these quantities are evaluated for birth and death processes. So, for example, example 6.7 just gives us the formulas. We see that expected value ti is just equal to 1 over lambda times 1 plus mu expected value ti minus 1. So we get this recursive sort of definition of the expected value of ti. And of course, expected value t0 is very easy. It's just 1 over lambda. Therefore, expected value of t1 is just equal to 1 over lambda times 1 plus mu times 1 over lambda. And when we add those two up, we get that the expected value of the time to go from state 0 to state 2 will just be 1 over lambda plus 1 over lambda, 1 plus mu over lambda. And sort of I refer you to the book for the sort of full derivation of why this is the case. The book actually does it for general birth and death processes where things are not so easy. And this is sort of the application of the general formula that they derive for the simple case where lambda I is identically equal to lambda and mu I is just equal to mu. So, yeah. And similarly, you can just check the formulas for the variance. Of course, since t0 and t1 are independent, and now we look at our book again. Okay, now page 3. It's a pretty messy formula. So variance of ti is equal to 1 over lambda I mu I Okay. So we just apply this formula in our case. So apply formula for variance of T0 is just 1 over lambda squared, and lambda 1 equal lambda 0 equals lambda 1 equals lambda, right? Yeah, just lambda. And mu 1 equals mu 2 equals mu. And after you do all this stuff, you get what's in the answers. I think I'd be wasting your time if I wrote it down. Are there any questions about this? This is just sort of, looking at the formula. It's not very, just following the formula. But there's a third part to that question, though. So in the long run, what proportion of time is there a working machine? That's the same deal as what we did before. So here, P0 is just 1 over 1 plus lambda over mu plus lambda over mu squared. And P1 is equal to lambda over mu times P0. P2 is equal to lambda over mu squared times P0. So, So we're interested in, we want at least one machine to be up, right? Is there a working machine? Yeah. So this would just be P0 plus P1. Because P0 means that both machines are good. P1 means that only one of them is bad. So that's the probability that we're interested in. Any questions? Everyone's comfortable with this? Good. Okay. So 23 now. Yet another variation on the same problem. So now we have a job shop with 3 machines and 2 repairmen. The amount of time a machine works before breaking down is exponentially distributed with mean 10. If the amount of time it takes a single repairman to fix the machine is exponentially distributed with mean 8, then blah, blah, blah. So we have a job shop, 3 machines, two repairmen. So let the state be the number of machines that are down. So Okay. So now again, this is a birth-death process. And now it will be a little less trivial to figure out what the birth rates and death rates are. Okay, so now are they all working at the same time? Yeah, so they are all working at the same time. So let's see, what is lambda 0? Well, let's first do this stuff. Okay, so we know that each machine works for, okay, so each machine, the lifetime of each machine is exponential with mean 10, so its rate is 1 over 10. But now, since now the three machines are working at the same time, we're interested in the minimum failure time of these three machines. So that we know, again, will be exponential, and it's the minimum of three exponentials. So it will be an exponential with the rate being the sum of the rates. So it'll just be 3 over 10. Similarly, lambda 1 will be 2 over 10, and lambda 2 will be 1 over 10. Because now we only have, one of them is not working, so it's the minimum of 2. Yeah?
Oh, no, sorry. Different question,
All right. Yeah. So now we know that the birth rates, let's figure out the death rates. Well, when only one machine is down, one repairman is working, so we know that he works at a rate 1 over 8, because his mean time is 8, so the rate is 1 over 8. Now, when two machines are down, this means that two guys are working. So again, it's the minimum of 2 exponential, so it would be 2 times 1 over 8, so 2 over 8. And when three machines are down, well, we only have 2 repair people, so the rate will still be 2 over 8. It just means that the one that is sort of extra is not being attended. So now, given all this stuff, it's easy to figure out the probabilities, right? Like normally, this is sort of the tricky part of the problem. Once you've done this, you know how to solve it. So, I'll sort of spare you the algebra and just give you the results. Okay. So this is what we get if we do, if we apply the generic formula. So what is the average number of machines not in use? Okay. So it's 0 times P0 plus 1 times P1 plus 2. Oh, not in use. Yeah, plus 2 times P2 plus 3 times P3. And this gives us an answer of this. Now, we want to find also the proportion of time that both repairmen are busy. Well, this would correspond to either 2 failed machines or 3. So it would just be P2 plus P3. So I think that's basically it. Yeah. Are there any questions? Yeah.
If we made the state space the number of working machines, we'd still be able to solve it the same way. We just answer the questions.
Yeah, it'd probably be, yeah, I mean,
The other way around.
yeah. Yeah. Yeah, I guess you would just set up sort of a different kind of birth-death. Like, the rates would be a little different. But you'd ultimately get the same thing. Yeah?
Would it be, oh, never mind. I was thinking, would it still be a birth-death process the other way, but it would be.
So what the question was, would the number of if it was the number of working machines, would it still be a birth-death process? The answer is yes. Yeah. So now let's do the last problem. But this is like kind of the more natural way to define it. It's the number of machines that are down. Okay. So now we have an ergodic MMSQ. Q in steady state. And I guess, what do we want to prove? Yeah, so the question is, what is ergodic? My answer is, it's kind of a very complicated mathematical thing that even I don't know exactly. But it basically, if something is ergodic, it means that it admits a stationary distribution. So remember in the Markov chains, we said that if a Markov chain is irreducible, positive recurrent, and aperiodic, then it has, stationary distribution, the pi's, blah, blah, blah. Now, those 3 conditions in the case of the Markov chains were what we call ergodic. So that's kind of the one thing I can think of. But it basically, it is the conditions that are necessary for something to admit a stationary distribution, to be sort of stable in the long run. So for example, a random walk, a symmetric random walk will not be ergodic because there is no stationary distribution. It's because it's null recurrent, it goes everywhere, and there's no probability distribution that can capture sort of the probability of it being in a specific state after a lot of time. So, yeah, so that's ergodic sort of. But the important thing to know is the properties of ergodic things, because that's what you end up using. So, an ergodic birth and death process. So, the MMSQ, you know, the MMSQ is a birth-death process. And by theorem proposition 6.5, so proposition 6.5 tells us that an ergodic BD is time reversible. So in particular, an ergodic MMSQ is time reversible. Okay. And now what do we want to argue? We want to argue that the number presently in the system is independent of the sequence of past departure times. Okay. So I'll do my best to explain this, but it's a little fuzzy even for me. So what time reversibility sort of implies is that the forward process. So in this case, the output of, or the arrivals into the MMSQ, so the forward process, is equivalent or is probabilistically the same to the to the reverse process. So in other words, you know, now forget about sort of what this system exactly is. You have a queue. You have some process going in, say the arrivals at time t. And you also have the departures at time t. So sort of what time reversibility implies is that, you know, you're looking at the forward process, which means that arrivals come and then they leave. Now, if you were to sort of start playing it in reverse, like say, you know, it's like you have a video player or something, and you start doing the whole thing in reverse, where now departures correspond to arrivals, and arrivals correspond to departures. So if you were to do this, then this process would be the same as the forward process. So I know it's very kind of fuzzy math type of thing, but I'm flip-flopping. But so yeah. So therefore. So since the arrival process is Poisson, the departure process will also have to be Poisson. Due to so now So now since the departure process is Poisson, and since in reverse time departures correspond to arrivals, we must have that yes, by the Markov property. Okay, that the number in the system at time t is independent of what happens in the future, or of what's happened in, future arrivals. The number of number n So that's kind of what's going on here, because since the reverse process will also be Poisson, then so the number of people who are in the system will sort of be independent of what happens in the future. Now, the future in the reverse time corresponds to departures. So I know it's. But that's sort of, I mean, it all sort of hinges critically on this process being time reversible. Actually, yeah. So I know this is it's not very rigorous, but it's the only way that I think we can argue it. So, any questions? Any general questions before the exam? Well, okay then. Thank you.